So I've mentioned it before and I'll say it again. Mathematics isn't about trying to get to right answers. It's about being creative with your approach and finding ways to change your perspective so that you can discern a truth that wasn't immediately apparent before. And I want to show you an example of that. So I take teaching very seriously. I'm a career changer. I used to be an engineer. I gave a position that had quite a lot more benefits and pay and such because I really enjoy teaching. And I believe that if I can show people the power of mathematics, that they will be able to take better control of their future, their careers, and that we will all get to a better place. And I want to show you how I try to take that one step above just presenting material. So I do a lot of analysis on how I present and how the performance results are for tests and how performance results are for homework. And I try to compile that all to determine exactly how students are behaving so that I can make adjustments and changes semester over semester to give you the best experience possible. Now, this is an example of some research I was doing not only for my classes, but actually as part of my graduate program, my thesis. And my thesis was all about trying to explore how students learn, what the best way to do homework is, what the best way to do testing is. And I was at the time using a Khan Academy system. So Khan Academy, in my opinion, is a wonderful system for having homework and having resources and supporting student learning. And you can see here that I've got students' grades that I just collected here. So I've got all the different grades and they're color coded. And then here I've got their midterm scores and I've got their test 1 scores and their exam 1 scores. So I've got the grades they were getting on their homework essentially are right here. And the grades that they were getting for their tests are over here. Now, my question that I had was, is my homework being effective? I had been using a system that few other classes were using at the time. Actually, no other classes were using at the time, so I didn't have any data to compare against. And I wanted to know if students who were spending time in my homework system were actually getting better at the work, or if they were still the same level of understanding and it was just an unwarranted burden on them. And so here's what I did. I took all this data, and I thought of it as I would in algebra, as a point. So for example, if I wanted to know a student who was getting a 98% on their homework by the time of the midterm, and they got a 98% on the midterm itself, I was saying, okay, well, let's look at the homework and say if I give a question of what does a 98% on the homework get me in terms of a midterm, I said the answer would be a 98%, at least for this one data point. And then here I looked at it and I said, okay, well, let's do that for each of these. So here I'm getting a 64% on my homework, that gets a 61% on the midterm. Let's look down here. Here, there's a couple of places where there's a disparity, right? Like here, an 84% got a 93% on the final. Or some places I got 66% on the homework, but I only got 55% on the midterm. And so I started to look at all these as points, as coordinates on a picture. And so all of this data can look intimidating, but if I put it into a picture, it becomes a lot clearer. So here we have all that data where it's plotted in a picture. I've got the Khan Academy scores over here, and I've got the test scores here, and I did this for the midterm, which you can see in blue here, versus test 1, and I can see that both of them are very much of lines. It just appears like one of them has a different slope than the other. In fact, by the time you get to the midterm, this blue line, it looks like the impact of studying and doing those last little bits of the homework actually has a larger slope, a larger effect than it did even back at test 1. So it looks like as we get further and further into the new material, the people who are maybe doing well because they had a good job or a good foundation in the last math class, they were starting to fall a little bit behind if they weren't keeping up with the homework. And so here you can see that slope becomes steeper. So in other words, the more that you get higher on your Khan Academy, every step you go over higher on the Khan Academy causes you to go even higher on your test scores. And this is really useful information. But the truth is that this actually wasn't all of the data I started with. I actually started with data that didn't look like it was in a line. And if I wanted to try to make it look like a line, I had to get rid of all the scores that were less than 40%. If you include the scores that are less than 40%, you actually get something that looks just like this. So here is the line of demarcation, so to speak, this 40%, and you can see that this data point right here is this data point right here, and all of these three, this orange, blue, orange, is this orange, blue, orange right here. But I had a few of these outliers, and these outliers didn't fit my line. You can see that my line would have come through right here, and it wouldn't have looked really good with these last ones. The model wouldn't have fit. But that made me think, maybe the entire description isn't actually linear. Maybe it's actually quadratic. And that makes me think a little bit deeper. Maybe it's not so simple to say that students who get high scores on their homework get high scores on the test. Maybe there's a few over here that have a different story that they're trying to contribute. And so here's what I think. I think that there's two types of students. There's the students who don't do their homework because they think that they already have all the knowledge they need. And those students kind of fall out in one of two different ways. So here's the 0% on the homework, the people who didn't even start their homework. And how did they do? They got 50%, 60. Like they got a little bit below D's, maybe some F's here. And that's kind of what happens when somebody thinks that they're too good for the homework, is they usually have quite a bit of knowledge, but they just don't have enough to get the score that would allow them to pass the course. And then you get some people over here who only kind of attempt the homework a little bit. You've got some people who are getting 20s and 40% on their homework. And what's the result of that? Well, sometimes you get some people who are up here in the C range. Sometimes you get some people who are doing pretty badly. So these are the students who are really struggling, but they're not really doing anything about it. And then over here, you've got the students who are trying to complete most of the homework. And for every little bit they do more, they get better and better on the test. And this is where most people fall. And so when you put it into a picture, you get a really interesting story of saying most of the time, if you want to do well in a class, you need to work on the homework. But if you don't work on the homework, you have a couple of different things that are going to happen. Either you're going to do pretty okay because you just have a strong skill set, but it's not going to be okay enough for you to pass the whole course. Or if you're not doing the homework because you're intimidated by it, then that's only going to result in you having a tough time on the test as well. But if you treat your studies like a student who's successful, if you want to get an A, you need to do what students who get A's do. And the students who get A's on their test work really, really hard to make sure that they're getting A's on the homework and they're picking up those last little bits of information. So this is something I would have only found out or thought about if I was drawing it as a quadratic, versus if I talked about it in the simple perspective of a line of just saying do more homework gets you better scores. It's not horrible, but it's not exactly the whole story either. And this is really the power of being able to model with different types of equations, is that sometimes if you're not intimidated by the fact that things look different than a line, you can pick out a little bit more detail, a little bit more information than the other people who are looking at the same problem as you. Now, the goal of this lecture is that by the end of this, we'll be able to look at a real life scenario, one that I've found, and we'll be able to recognize what's happening behind the scenes from a place of understanding, and really be able to see how all of this graphing, all of this function, all of this equation practice that we've been playing with has a role in the real world, but only if you choose to apply it. So let's take a look here at a few of these equations that are very common in the real world in terms of modeling, as well as in the physical sciences. These pop up all the time in physics. And these are equations that you're really going to want to start to become familiar with, to the point that you could know them, you could apply them, you could recognize them. So if any of these feel a little bit weird as we run through and do this quick review, spend some time on it, pause the video, take a look at it until you really feel like you could explain this to somebody, but maybe even more than that you really feel like when you get out into the professional world, you'll be able to recognize and say, wow, that's a trend that's linear, that's a trend that's quadratic, that's a trend that's an absolute value. And we'll talk through all of those as we go through here. So let's first start off with what it means to be a constant function. So we're going to do this pretty quickly and pretty broadly. So we know that is where my function is dependent on x, but really the function that's dependent on x doesn't have anything to do with x. No matter what x is, I'm always going to be equal to a constant b, where b is just some number. So you can think of this as just being some number. So it says, no problem, you want a program where anytime you put in x, I'm going to give you out some number. Well, we know what the shape of that is. That's going to be a horizontal line that says no matter what x value you have, no matter what question you have, you're going to go up to some amount of b, wherever b is. Maybe it's above the axis, maybe it's high up, low up, maybe it's negative, whatever. And we're just going to go up that high and put in a dot. And we're going to do that no matter what x value question you ask me. Here's another dot, and so all the way across and all the way through this entire picture, you're just at a height of b no matter what question you ask. This is what we refer to as a constant. You can recognize it as a flat horizontal line that runs directly through y equals b, because that's really all that we're saying here, is that f of x, the result of my function, is going to be equal b, and if I want to draw that into a graph, that would be a height of b every single time I plot a point. What about a linear function? Oftentimes we look at this as a positive slope, but we could look at this as a negative slope as well. So really what we're talking about is we have an intercept, again, at b, so we'll go ahead and draw that in somewhere and call this b. And then we'll say that I have a slope, and my slope is m. And just to kind of spice this up a little bit, we'll say here's my point, and maybe I can even talk about this line as having a negative slope. And we'll say, no problem. What does m mean? M is the ratio of my change over in my x, I'll put that as a little delta x, to my change in y. And we can always write that in as saying my change in y divided by my change in x is going to be equal to m. So here we have it, that's our slope. You have your intercept, which is b, and that's all of the information that I have right here is that ratio and a starting point, some kind of starting point. Now remember that not everything is always going to appear in this form. It could sometimes come in a point slope form, it can sometimes come in a standard form, and you might need to work it back to get to here to be able to graph it so easily. But linear functions will always get you a linear picture on the graph. In fact, even the constant function up here is a linear function. It just has a slope of, well, I guess I'll leave that for you. How many x's do you see up here? If you have any questions, let me know. Let's take a look at the square function. So square function is one we've used a lot. Squares pop up all the time, not only in geometry, but they actually pop up in physics. If you want to talk about gravity, you want to talk about magnetism, you want to talk about electric forces. If you want to talk about the planets rotating around, or if you want to talk about the expected patterns of microscopic or atomic level particles all moving around, all of these can be described using a square function. So these are going to pop up a lot. And it's just as easy as saying that anytime you want to start with a value for making your square, you're going to make a square that is resulting from that value times itself. So for 2, it would get you 4, for 1, it would get you 1, and for the negative values, a negative times negative, we use our logic model to help us think about what negative squares might be, and we say, no problem, negative times negative would give us a positive, and this is going to be our square. It's our parent form, or our starting place of a parabola. And we can do a couple of quick little gut checks here. First of all, let's look for that y-intercept. That y-intercept's at 0, and that would make sense because if my x value is 0, all I'm doing is getting 0 over there. So it makes sense that I'm going to have an intercept here at 0. And it looks like it's going to be growing whether I go to the negative or positive, and that would make sense. It's going to be increasing this way, it's going to be decreasing this way. Okay, great. The cube function. The cube function looks just like a little s turned sideways, and so it comes from saying I've got -1 cubed would be -1 times itself, so there's 3 of them in total, so -1 times -1 times -1 is going to give me a -1. If I do that for a positive 1, that's 1 times 1 times 1, 0 times itself, a whole bunch is 0, so it might start to look like a line, but in truth when you get out to 2, that's where you have 2 times itself, so that there's 3 times itself in total. That already gets you all the way up to 8, so this thing just skyrockets on up. It skyrockets on up, it comes down here, it slowly kind of creeps in, and then again it skyrockets on up with a -2, causing it to drop all the way to -8. And you can think about what's happening here in this inner part by just considering a few different things, like 1/2. What would 1/2 times itself 3 times? You'd say, well, 1/2 times itself would be 1/4, times itself would be 1/8. So it turns out that in this small little gap between -1 and 1, if you have a number there and you multiply it by itself over and over again, you actually get a smaller number that results. But if you start with a number that is in the 1 area or bigger, then that's going to be something that has a larger value that results. Kind of an interesting fact about thinking about fractions. When you are multiplying fractions over and over, they get small real quick, but if you're multiplying numbers that are bigger than 1 together, they get really big really quick. All right, absolute value function. Remember that our absolute value function talks about our distance away from 0. So this is a pretty good one to graph. We can talk about at a value of 1, how far am I away from 0? And you'd say I am 1 away from 0. That makes sense. At 2, I am definitely going to be 2 away from 0. And at 3, I'm going to be 3 away from 0. At 0, I'm going to be 0 away from 0. At -1, I'm going to be 1 away from 0 again. And 2, I'm going to be, again, 2 away from 0. So we get this kind of linear looking picture, but it takes an abrupt turn right here where all of a sudden all of my negative values turn positive. And so this one has the same kind of thought that we could run through with the cubic function, but now we have to be careful to say that I'm going to have an abrupt change. And to justify that, perhaps we want to look at it by saying, what would it have been if it was negative and then we made it positive? So if I had first said that -1, I say -1 is a negative distance, but and then I need to make it positive. So I can do this in stages and think through everything as I'm drawing it out. -2 is a negative distance. No, that makes no sense. It's a positive distance of 2. And so what you had was something that would have trended in the manner of being a line, but really we can't think of negative distances, so all these points get reflected up the moment I cross over that y-axis. Kind of interesting when you think of it this way. All right, square root function. So if you need to, you can go back through and you kind of put this in a little note to yourself, or maybe erase some of this so it's just the points that you're playing with and saying, oops, it would have been here, but I guess that's not quite right. We need to move it on up. We'll put a little picture here. Now I'm just getting artsy. Okay, great. What about this square root function? Well, we can think of the square root function as, again, look for numbers that are easy to plot. We could think about what's the square root of 1. That should be something that's pretty easy. Square root of 1 would be what times itself 2 times gives me 1, and we'd say 1, no problem. For 2, we could say what times itself 2 times gets me 2. Difficult question, let's skip it. What times itself 2 times gets me 3. Difficult question, let's skip it. What about what times itself gets me 4? Oh, that'd be 2, no problem. I'll put it right here. And now at this point, we've already played around with the idea of parabolas being our square. Then now it really looks like it's like a square, but it's a square that's I'm growing sideways as I would have wanted to grow up and down. And here's what I mean by that. Take a look up here. This one had the same shape, but I was looking for the nice numbers like 2 to get me 4 and 1 to get me 1. Here I'm doing the same thing, but I need to look at it in the reverse order. Now I'm looking for 1 to get me 1, and I need 4 to get me 2 instead of 2 to get me 4. It's like I'm flipping the conversation in my head, but it's all things we played around with. It's just a different way of looking at them. So this is almost like the where did it come from graph. This is the where did the square come from graph. What about the cube root function? Well, again, let's just do the easy numbers, plot it out, and then think about it in comparison with the graph we had before. What cube rooted, so what is the cube root of 1 would be what times itself 3 times gets me 1. Again, I guess that'd be 1. And what times itself 3 times gets me 0. I guess that'd be 0. That's pretty good. What about 2? What times itself 3 times gets me 2? Don't like that question. What times itself 3 times gets me 3? Difficult question. What times itself 3 times gets me 4? Difficult question. Same thing with 5. Same thing with 6. That's a little annoying. But I could jump ahead and say if I was able to get all the way up to 8, I'd say what times itself 3 times gets me 8, and it would have been 2. So for 2, I could start at the height of 2, and then I'm just going to try to run all the way over to 8. It's off my paper, so I'm going to have to kind of just draw it as if I'm extrapolating. And so we'll draw it like this, and then come on in. Looks almost the same as my square root, interesting enough. But whereas before, I could have said with my square root, for example, what times itself 2 times, or what if I have a value of -2, what's the square root of -2? And you'd say that doesn't exist. That's why we had to stop it the moment we got to 0. The moment we started asking questions about these negatives, we would have gotten weird answers, like what happens when I try to put in a square root of -3? No answer, no solution. So there's no height that I get when I come over to 3 and look for a height. That's why the graph stops existing. Does the same thing hold true with a cube root? For example, what's a cube root of -1? What times itself 3 times gets me -1? And I would say, again, that'd be -1. So if I go over here to the -1 and I say I'm going to try to do the cube root of -1, you say this time it actually works. This time you actually get an answer here. And I said, okay, well, what's the next thing that I could easily cube root? And you'd say, well, probably whatever gets me an answer of -2, and you'd say, well, that happens from the cube root of -8, so I guess this must be my x value, just like it was in my original, and this is my y value. So let's play around with that. I go to a y value of -2, and then I run all the way across off the paper to -8. That's some kind of point way out here, and then I connect them all nice and pretty like. There we go. That's going to be my cube root function. Pretty cool. All right, reciprocal function. This one, we again have seen it in complicated versions. We've seen it in not complicated versions. There's a few things going on here. First, I have an x in the denominator. That's always a risky thing because there's a certain value you can't divide by, and that value is 0. So if x equals 0, this entire thing's going to have some trouble. So I can already say I'm going to put in some kind of dotted line here right on top of the axis and say that when x is 0, we're not going to get an answer. But I could try some other values, like maybe making it into a table. I could have done a table for the other graphs too now that I think about it. So I could have said, okay, well, what if x, which is I'm going to put here, and I have f of x, which goes here. I could say x equals 1 would get me 1 over 1 equals 1. No problem. I'll go over to 1, I'll go up to 1, and I'll plot a point. And then I'll say, well, what about 2? That would be 1 over 2. That would be equal to 1/2. That would get me 1/2 right here. No problem. What about on the other side? -1 would be 1 over -1. So I've got, oh, that would be -1. So -1 comma -1 would put me right here. And then the next one would be if I put in -2, that'd be 1 over -2 gets me -1/2. So -2 down 1/2 puts me right here. Now this might feel a little bit weird. You might want to try a few more, like some fractions, because it looks like it's difficult to figure out exactly what this trend is. But after trying it with 1/2 and trying it with maybe -1/2, let's do that. Why not? We'll put in 1/2, and then that'll be 1 divided by 1/2. Well, if I split 1 into halves, I guess I have 2 of them. So that would be 2. And you could also check this by using that rule, which is that when you divide by a fraction, it's like multiplying by the reciprocal. So, okay, 1 divided into halves gets me 2, and then 1 divided into negative halves must get me the opposite of 2. So, -2. Okay, so that I guess would be at 1 gets me 2, or 1/2 gets me 2, and -1 gets me -2. I think we start to see a little bit of our structure here. When you graph them all out, even if you need to find more points, you're going to get a graph that looks just like this. It's not going to have an answer at 0. It's going to end up skyrocketing on up. And on this side, it's going to start from a very negative place, and it's going to come back to that axis where it's going to hug it. And let's think about why this is again. Because if I put in x values that are big, then that's 1 over a big number. 1 divided by a big number, like taking 1 pizza and dividing it by the state of Illinois, is going to be a very small amount for each person. So it would make sense that as I go to bigger and bigger numbers, my height will get smaller and smaller. As I start to divide things by smaller and smaller numbers, though, if I divide by a small number, I'm actually going to get a very big number. And so that's going to happen on the positive side, it's going to happen on the negative side, and then the exact same thing is going to happen over here. If I look at the opposite of dividing by the state of Illinois, then I'm just going to get a negative small number. So start to make sense of these and really understand where it is that these equations are coming from and why it is that they're graphed in such a way. But once you've got an understanding of all these, it's really about trying to apply them in a comfortable way, building up our familiarity with these, and to work through finding efficient and quick methods of solving through problems. Because after all, we don't want to have to reinvent the wheel every single time. We want to learn from our first mistakes, put procedures in place so that next time we can get through the problems faster, get to more insight, and really develop our knowledge. So let's take a look at this one here. How would you graph f of x equals x squared for x greater than 0? Well, we know how to do x squared. We know it's going to be that U shape. Check it earlier in your packet if you'd like. We know that it's going to be something that's going to look quite like, like this. We'll put a little sketch here and a little sketch here. It's going to look just like that. But I only want to graph it for x greater than 0. Ooh, okay, I guess in that case, I can't use x values. In other words, I can't use these horizontal distances that are less than 0. So let's go through and let's erase that. I can't use that part. And I'll take this away. Did I get it? Is this it? Well, let's check. It looks like I've got something above my 0. Does that work up here? It does not. See, if I have something that's right above 0, then that doesn't mean x is bigger than 0. That means it starts at 0. And I've got a little conflict there. So maybe I want to start it at 1 instead, x equals 1? Like this? Well, no, that doesn't quite make sense. There's some fraction values like 1/2 here that are bigger than 0, but I don't have a graph above them. Okay, so we need to use 0 as our reference point. Oh, this is just like when we were doing interval notation. I need to find a reference point. Here my reference point is 0, and then I can just choose not to include 0, and I'll include everything just immediately after that. And there you have it. It's the structure of the x squared graph, but it has a boundary at 0 that I don't include. Okay, how would that compare for here, where I have x is greater than or equal to 0? Well, again, it's going to have the reference point is going to be 0. And it's 0 because I'm putting 0 into this whole thing. So 0 squared gets me 0. So a distance away of 0 gets me a height of 0. So I'll put a circle there for my reference point. And then I'm looking at the structure of x squared, which I'm going to draw in. But since it says that I'm including that reference point, I guess we can shade that part in. And so this is a way that we can notate the exact structure we're paying attention with a restricted domain. And this is the thing that, again, you're going to want to use often whenever you're modeling. You remember earlier when I showed you that quadratic equation that I used to model my students? I had to think to myself that I was restricting the domain in that example. After all, my students didn't have negative homework scores and they didn't have negative test scores. So really I was saying that I just wanted the structure of a quadratic, but I needed to make sure that I was communicating to everybody that the structure only extended as far as 0 and no further. Okay, great. So let's see, model the following graph using an equation or combinations of equations. So now we've really got the skills that we need to consider what's something like this? What's it look like? And I want you to take a moment and ask yourself, what exactly does this look like? If I had to look at pieces of this that I recognized, what does it look like? Now, what I recognize here are two different things. And I'm going to try to use both of them to model. The first thing I recognize is that this shape looks familiar to me. Just this part, not this part right here, just the first part. The first part looks like a line. In fact, this looks like another line, but a different line. So it's almost like I'm imagining that hidden behind the scenes is some kind of reference line that was here going all the way through, and then there's another one here going all the way through, but then I just took the domain and I restricted it. I said I have to cut off this bit and I have to cut off this bit, and really I got to cut off this bit because I only go as far as 1, and I got to cut off this bit because I only go back as far as -2. And I say, well, there's some lines there. Let's see if we can describe the lines. Okay, well, let's describe this line first. The first one seems to be a line that has a slope of going down 2 and over 2. So I can write that using my y equals mx plus b format. That would be going down to a drop of 2, or a rise of -2 over 2x plus my b, my intercept. And my intercept here looks like it's 0. So I could say that this first part right here could be modeled with the equation y equals -x. Interesting. What about this one right here? This one here looks like it could be modeled similarly, and this one has a positive slope. The positive slope is going up 1 and over 1, so I guess that would be y is equal to up 1 over 1 times x plus a y-intercept again of 0. So the second part is y equals x. Now we start to see a little bit of confusion. If I say, what is this graph? You're like, oh, this graph is y equals -x and y equals x. This is confusing to tell people, because what this looks like is that it equals, that -x equals y and y equals x, so that -x must equal x. Nah, that's not quite right. It's really like I've got two different pieces of a function here. I guess I could describe this using function notation. I always like that better than y. So let's see if we can put that in. Function notation would say I have f of x is equal to this and f of x is equal to this. Oh, but that's not exactly true, because it's only equal to this sometimes and the other thing sometimes. So it's equal to this -x between an x value of -2 and 0. So I guess I could write it like this, x value between -2 and 0. In fact, it works all the way up to 0. It doesn't work at -2 because there's an open circle there. Okay. And then this one picks up right after 0 and goes all the way until an x value of 1. So it's like I really need to capture that both of these are happening. That it's this thing in the top sometimes, and it's the other one other times. Well, that's where we get some creative notation, and we say, well, if f of x really is talking about both of these, then let's clean this up a little bit and show people that sometimes f of x is both of them, where it's one depending on some of the x values, and it's the other depending on different x values. Now, there's an important thing we need to keep track of here, and that is if you say that a function is dependent on one thing sometimes and the other thing other times, in order for it to be a function, you can't have there be any overlap. There can't ever be a time when it doesn't pass that vertical line test. In other words, there can't ever be some ambiguity. If I give you an x value, I need one and only one output, one and only one f of x value, or one and only one height that pops out of that equation. So here, there's no risk of that. If x is equal to -1 or -1/2, or negative anything that's between -2 and 0, I'm going to use the first part. And then if I am at 0, I use the first part. And if I am anything right above 0, I immediately jump to the next part, because everything greater than 0, I'm going to be down here, and that's going to go all the way until 1. So there's not a single x value that's represented on this picture that's going to be confusing when I come down here and I write it in my function notation. So take a moment and pause the video. I want you to try to explain in your own words what you think is meant by all of this. Notice first, there's an interesting hidden detail. This part right here, we'll read together. This says that f of x, let's just imagine these two parts, f of x is equal to the opposite of x whenever x is negative, and the regular x whenever x is positive. But for some reason, people are saying that you could have also described this using an absolute value, that an absolute value is all of this stuff too. Are these really all the same? Well, let's think for a moment. What does an absolute value do? If I took a negative 3 and I did an absolute value of it, I would make that 3. So let's check in this equation what we would have done. If x is negative 3, would I have looked at the top part or would I have looked at the bottom part? So I'm going to say I'm going to look at the top part because negative 3 would be an x value less than 0. It's not an x value greater than 0, so the bottom part doesn't apply right now. At negative 3 only, I would use the top part, and I would say, no problem, let's plug it in. And it'd be like, no problem, there's a negative from the structure, and then I'm going to input my x value of negative 3. Negative 3 would get me positive 3, and sure enough, that's the same thing as the absolute value. Well, let's try that with another one. Let's try that with, imagine if instead of negative 3, I put in negative 200. Okay, if I wanted to put in negative 200, again, all we're playing with is saying what's f of negative 200. And the claim is that that's the same thing as the absolute value of negative 200, which is the same thing as the function result from all of this. Well, again, I would use the top part of the function because it's negative 200 is less than 0, and that would cause me to put negative 200 into this negative structure, so I'd have negative 200, and sure enough, again, it would work out just fine. What about a positive value? F of 300, for example. F of 300, by the claim here, is that that's equal to the absolute value of 300, which is equal to, I guess I wouldn't use the top structure anymore because x isn't less than 0 anymore. I guess I would now be looking at the bottom structure, which says I just need to write my x. I guess that's just 300. Oh, and lo and behold, it works. This is what's called a piecewise function, and piecewise functions are a very useful way of describing very complex models that rely on other bits and pieces to help get the entire message across. So for example, if you were going to explain absolute value to somebody, I think at the beginning of the semester, you probably would have said, it is making negative things positive and it's making positive things positive. In other words, it's finding the opposite of negative things and leaving positive things alone. Notice that that's everything that's written right here, is that absolute value is nothing more than recognizing that if things are negative, I need to do the opposite of them, and if they are positive, I need to do nothing to them at all. So this piecewise structure allows us to talk about if and ors and thens in a much more organized way than just writing out a complete sentence. And I bring this up because in the problem we did before, there actually is the opportunity to have modeled this all a little differently. Some of you may have recognized that this structure up here actually looks a lot like our absolute value graph. And so you have two correct answers as far as I can tell for this. One is that you can say that you could model this entire thing using a piecewise, or in other words, using a use this sometimes or that other times approach, like this one. Or, if you're clever, you could recognize that you could have just as easily described it as being f of x equals the absolute value of x, so long as x is between negative 2 and less than or equal to 1. As it turns out, both of these things say the exact same thing as each other. So let that sink in for a little bit, play around, and recognize that when you are modeling, it really is up to you to be creative and to say, over what areas am I considering, what's the model, the structure that's behind them, and then to go back and test and reevaluate and retest, and then look out to other people and to see if they found even more elegant solutions. Now, I'm going to leave this one here for you. There's just a small little detail here, small tiny detail that's different between this whole thing here and this whole thing here. And I'm curious about whether or not that detail matters. And I'm going to leave that to you as a question. Does it matter that I switched that little detail on you? So first, this is going to help to train you to look for those small little details. See if you can find out why this whole thing down here and this whole thing up here are different. And then ask yourself, did that matter? Because I think there's actually a hidden third way that you could have described all of this. And maybe even a fourth way to have described all of this. Play around, be creative, and let me know if you have any questions. We do want to get some practice of interpreting these piecewise equations and putting them onto a graph so that we can recognize them for the future. And again, this is when we're hearing somebody claim that there are a lot of different rules that play in our model. Sometimes I do, and then other times I do differently. These are the kind of examples we're playing with. And these do, again, pop up quite a bit. I'm going to show you an example in just a moment here of how this happens in the US tax code, for example. You're trying to explain lots of different things, and you're trying to tax lots of different people who all have lots of different conditions. Sometimes you need to have models that talk about do this sometimes or that other times. So let's take a look. Here we have a lot of information to break down. This says that my function f of x is going to be determined by a lot of stuff, just a lot of stuff. And so we're going to look through this and say no problem. Well, it looks like f of x is going to be determined by the number 1. Sometimes it's going to be determined by the number 1 for all values that are less than 1 or less than -1. Okay, so here's the way we can think about that. We can try to draw all that in. So we say, okay, no problem. I've got a structure here. The structure is that constant structure, so I'm just going to draw that in, and I'm going to draw it in as being f of x equals 1. So notice that there's a lot that I'm picking out here. I'm going to try to draw this all out and expand it. So the first piece of information we found is that f of x equals 1 so long as, and I'll put a little comma, so long as x is less than -1. Okay, so let's draw that in. F of x equals 1 would be a constant graph that goes all the way through 1 and across my picture. But it says that it only happens for x values that are less than -1. So here, where's -1? Here it is, a little circle, and I need to talk about my reference value. And I need to talk about only things to the left-hand side of that. So I'm looking for things that are in this domain only. So that means everything above it has to be in this domain. Well, I think we drew this a little improperly then. Let's erase it and make sure that we don't go further over than our domain. So here we are, we can have all of this, but we have to get rid of the rest. And that would cast the appropriate shadow on the domain. In other words, that would include the appropriate x values as my questions. Good, so that's the first part. The next part says that I have a time when f of x is equal to the cubed root of x, but that only happens when x is between -1 and 0. Oh, I think it was this one, right? There we go, that's the cube root one. So again, I'm going to look at starting this at the x value of -1. X value of -1 puts me right here. That goes until 0. 0 is right here. So then we're going to erase this entire thing, add in that structure between the two places that are warranted, and then I can include the -1 only. The next one has to still be left alone. All right. What about this one right here? This one says that the f of x value is equal to 1 over x, so long as x is bigger than 0. Maybe I'm tired of writing it this way. Couldn't we just write this using interval notation as well, from 0 to infinity? Okay, so again, creative approach, use what you'd like. So between 0 and infinity, I have this structure. Well, that structure, if we'll do it maybe in orange, remember that that structure was this structure right here, like that. That was a little bit of a bad drawing, but we're going to go through this and we're going to say it's only for starting at 0, not including 0, starting at 0 and then going bigger. So I guess that would be where I look for the height at 0, which I don't really have, but then everything after that works out just fine. So I guess I'm including all of this right here that casts the shadow right here. Okay, and then we'll go back through and we'll erase all of our orange. So I'll erase my orange here, and then I'll erase my orange, and it's a little hidden there. And I'll take off my domain line so I'm not confusing. Very nice. So everything that I have in my picture here is another way of thinking about what I have here, where now in the picture, if I want to find out what happens at -3, it's like no problem. At -3, I just go up to the graph, wherever the graph is, and it looks like it's at 1. Or if I say, what about at 2? You say, go over to 2 and then go up to the graph, wherever it is at 2. Go at -1 down to where the graph is at -1. In fact, -1's a good example. Would I go up? No, there's no graph there. There's an open circle. I'd need to go down. Now, how would we interpret all of that if we were looking at just the numbers here? So we've done it in the picture. You can reference these in a moment. But I want to think about how I could solve some of these problems without having to go through all of this hassle of drawing pictures all the time. So let's find a faster way to do this. So let's look at the first problem that we have here, f of -3, and we're going to ask ourselves what this means. F of -3 means I have an x value that is -3, and I'm curious where the answer is. So we go up here into our structure and we say, I have -3, and you say, well, it's not as easy as just plugging it in. There's a lot of ifs, as represented by this little brackety thing. So, okay, which one do I go with? -3, is that going to be the first condition, the second condition, or the third condition? And we'd say, well, -3 is definitely less than -1, so I guess that's where I'm going to start. And I'd say, all right, that says that f of x is equal to 1, and I guess that's my answer. Notice that in our picture, that's exactly what we just said. We said that if you go over to a distance of -3, and then you go up to the graph, that's going to happen at -1. Go over to -3, and then we go up, that's going to get you right here to -1, no problem. Or +1, I get you, +1. All right, what about f of -1? Let's put that in. F of -1 would be equal to, when I look up here and I say, which condition is -1 less than -1? No, it's not. Is -1 between -1 and 0 with -1 included? Yes, it is. So we would say, all right, let's evaluate it using that structure. We'll do cube root of -1, which we then know is going to be equal to -1. And just like in our picture, that's the same thing as saying I want to go over to where -1 is and then find my graph. If I go over to where -1 is and I find my graph, that's right here at a height of -1. So there you are, checks off of the picture. What about the f value of 2, the function value of 2? Where does 2 get us? Well, just like in my picture, I would expect to go over to 2 and go up to my graph. But if I was looking at all of this only, I would go condition by condition and say, well, is 2 less than -1? If not, then I don't use the first part of all the information I have piled there. Is 2 between -1 and 0 with -1 included? Nope, it's a little too big for that. Is 2 bigger than 0? Yes, so I would say here is the thing that's going to apply right now, and we plug it right in. I'd say 1 over, instead of x, I'd put in 2, and that would be 1/2. So there we have it. And sure enough, if I go over to 2, I would go up to just about a height of 1/2. So now we've really been able to find out that with this structure, we can get answers immediately. We don't have to worry about drawing pictures, although we absolutely could. Or we can look at it in the reverse and say, if somebody gives us a picture like a bunch of data, or we get hired for a job to make sense of something that appears chaotic, we can apply all these structures to the scenario to really describe and predict and fill in the gaps between. And I want to show how we can do that with an example of something that's just absolutely complicated, and that is the US tax code. Now, the US tax code is complicated. It's really crazy complicated, and we're going to walk through it real quick here. First thing to know about the US tax code is that it is a progressive tax, which means that as you make more and more money, you get taxed more and more. In other words, if you make 0 to 10,000, and you can read this here, if I get a taxable income, if I make between 0 and 10,000, then I pay this amount as a rate for my tax. So for example, if I made 10,000, I would put that in here, 10,000. I would multiply that by 0.0259, in other words, 2.59%, and that would get me something like, what would that be, $259? And so that would be how much I would pay if I made 10,000. But if I made 25,000, then I would need to multiply that by 2.8%. And if I made over $150,000, I would multiply that by 4.5%. Okay, very interesting. How could we draw all of this in a picture? Because this is crazy hard for me to communicate to you, and we've been studying math all semester. What about people who aren't so mathematically inclined? How could we show them the behavior of all of this tax system without them having to understand the nitty-gritty details? And I would argue that we should do it in the form of a graph. So, what's the first thing? If I have between $0 and $10,000, then I take my value, whatever it is, X, and I multiply it by a number. Doesn't that look like a line? Isn't that exactly the structure of a line? Is that number times X would be like my slope number times my X in a line? Well, I think so. In fact, let's pull that out here. Really what I'm doing is I'm taking the income that I have and I'm multiplying it by 0.0259. And that's all that I have to do if I'm between 0 and 10,000. So I could even write that as this only applies between 0 and 10,000. I'll put 10K there. Now 10,000, it says I have to be over 0. Okay, so I can't be at 0. I got to be over 0. I'll not include it. And I have to be not over 10,000. Is 10,000 not over 10,000? Yes, so I guess I can include my 10,000 here. And then I've got the first part of all the details I'm doing here. That would be the first part of my whole big tax function here. Well, what about the next one? Between 10,000 and 25,000, that would be when I start at 10,000. I'll again put 10K because I'm running out of space. But it's over 10,000, so I guess this time I don't include 10,000 for this line, which makes sense because I include it for all of this stuff up here, and I go until 25,000. And at 25,000, 25,000 is not over 25,000, so I'll include that. And it says take a number and multiply it by 0.0288. And we can do this with each and every one. And we can group all of these together and call it my function for my tax code. In fact, I could even relabel it with something like the letter T if I really wanted to communicate to people that this came from a tax code. So I could call this the function T for tax, depending on X, your income. Well, let's take a look at what that would actually look like in a picture, and we can sketch that quickly just by using our intuition so far. These are all going to be pieces of a line. They're going to start somewhere and end somewhere. So the first thing I'm going to look at is things that start between 0 and 10,000. And we can say, well, at 0, if I plugged it in here, I would get 0 times this whole number would get me 0. So I guess that's where I'm going to start with a 0, 0. That's why I'll put an open circle at the origin. And then I say at 10,000, I would plug in 10,000 and multiply by all this, and I would get $259. And so I'd say, okay, at 10,000, I would need to pay $259. I'll put a little dot here. And I would connect everything between it with a line. I'd use that structure. And then from 10,000 to 25,000, I would have a line structure, but the only thing that's changed is I have a little bit of a steeper slope. So I would actually need to have my line be a little bit steeper. And I would say, well, at 25,000, where am I at? 25,000, if I plug it in here, I don't know. Let's pull up the calculator. My fingers are tripping all over my keys today. So let's do 0.20288 times 25,000. And that gets me $720. Now I'm only looking at that one point because that's all that I've determined I need for the structure here, is that if I go between these 2 points, I already know it's going to be a line. So why would I worry about in between values if I just need to know where I'm going to end up? So this is 700 and I think I said 20. Yep, $720 at 25,000, and I would go there and I would put in a closed circle. So closed circle here, open circle down here, but my open circle is filled in, so I guess that doesn't matter. And between this, I would connect it with a slightly steeper line. And as it turns out, I'm going to zoom out here. What you can really do is you can graph this entire thing by just saying that by the time you get to 150,000, a quick sketch would say that you had a very slow slope, and then that connected into a steeper slope, which connected into a steeper slope, which connected into a steeper slope, which connected into a steeper slope, and then went on forever for everything over that amount. And you could just go down here and say, what's really happening is that this steepest slope starts at 150,000, this slope right here starts at 50,000, this slope right here starts at 25,000, and this one right here starts at 10,000. And this is a great way of showing that if you make a large amount of money in the US, your tax rate is actually going to be quite high. But if you make a little bit of money in the United States, your tax rate is actually quite low.